You're listening to Inside the Logic, real talk with FPGA engineers. And today we're talking about one of the trickiest parts of FPGA design, clock domains. When different parts of a system try to talk on their own timelines, things can go wrong and sideways fast. My name is Kevin Rosenquist. And of course, I am joined by Ryan Erickson and Charles Sobczak. How you guys doing?
Doing good, Kevin.
Doing good. Thanks for having us.
Awesome. Well, glad to have you guys. I'm excited to hear some new information for me about clock domains. So let's start here. What exactly is clock domain crossing, and why is it hard?
Yeah, so to understand clock domain crossing, first you got to make sure you have a good handle on what a clock domain is. So in FPGAs, there are two different kinds of logic. There's combinatorial and there's sequential logic. The idea of combinatorial logic is you base some operation happening based on what some value currently is. And I know that doesn't necessarily make too much intuitive sense, but it's like the idea of, let's say you're holding up two thumbs up and your right hand is a thumbs down if the left hand is thumbs up. And so if the left hand turns thumbs down, the other one goes up. And so it's always the opposite. It's always dependent on what the other one is in this very moment. And so the idea there is maybe you have a circuit set up to where whenever one thing is on, the other thing has to be off. And the FPGA needs to understand that that value is opposite from the other. It's the same idea when people talk about computers speak in ones and zeros. It's all of that. Is it true? Is it false? If that's a zero, is that a one? It's the same idea. Sequential logic is something similar, but you take into account time. And so maybe my right hand being a thumbs up is only a thumbs up if my left hand has been a thumbs up or down for the last 10 seconds. And so maybe it takes into account of, okay, what was it 10 seconds ago? You know, there could be things that, like, maybe you have a traffic signal that checks to see if there was a car that passed through in the last 5 seconds. And then it might change to give the other side a green or something. And so it's very important in FPGA design to make sure that whenever you're making a circuit or a logic decision that you know that is it combinatorial, where it's a combination of inputs happening at the same time, or is it sequential, where it's a sequence of inputs happening at different times and taking into account of what operation needs to happen based on a certain timeline. And I say all that to say this, and FPGAs registers or flip-flops, which are single bit registers, hold values based on an instance of time. So there will be a clock, and you hear in like computers and CPUs, there's overclocking, some X gigahertz clock. In the case of FPGAs, it's typically on the magnitude of 100 megahertz, or sorry, hundreds of megahertz. You know, there's like 500 megahertz for the top of the line FPGAs and higher end arithmetic time frequencies. But so in FPGAs, the data in registers and flip-flops is latched and stored exactly on clock edges. And so the idea is that you can read the value from a register and it tells you whatever the value was on the most recent clock edge. So if a clock occurs every second and you read it a half second after the clock edge, you don't know what is trying to be put into the register right now, but you know what it was on that previous clock edge. And it's great because that means you can, if you have a register sending to another register, you can always know, in the case of an example of the clock being a second, you can always know that the first register is maybe 1 second or 2 seconds behind the next registers in sequence. And this is kind of an oversimplification of it, and I'm trying to keep it layman's here because clock domains can get really complicated really fast if you're not careful. And so the idea of clock domains is that you can have a group of registers or a group of operations inside of an FPGA where everything is happening either on the same cycle or on the same clock or on a group of clocks that are synchronized. So, like, for example, if in the example of a second, if something happens every second and you have other things happening on that second, then those two things are in the same clock domain. Now, maybe you have something happening every minute. That's still in the same clock domain as the same second because they're on the same clock, you know, the seconds into minutes. And so as long as they're basing on the same clock, maybe you have a clock on your watch or something that is doing some operation and maybe you're running for every, every minute you're switching between running and jogging on your watch, but then every 5 seconds you're taking a breath. Those are on the same. You're basing it off the same clock, so
Okay.
that's
Yeah.
the same domain. Everything is based off of the same clock. Now the problem is that let's say you're doing that, but then you want to also do something based on a number you're counting in your head. That's not the same frequency as with the clock that you're seeing. It's not the same. You're not basing off the same clock. You're not reading the clock. It's just a number that you're counting at some frequency. This disconnect makes it to where this other clock in this example inside your head you're counting is completely asynchronous from any clock that's based on the first domain, because the first domain is based on the clock on your watch, and in this case the second domain is based on the clock that you're counting in your head, which isn't necessarily a clock. But this analogy refers to, like, what if you had two systems or two FPGAs or two areas inside the same FPGA, which can get a little complicated, where certain operations are happening on clocks that are completely unrelated from each other. So let's say this is happening here and this other operation is happening at a different frequency. There is never a case of which you can tell with certainty that the data is occurring at the exact same time and the operations are occurring at the exact same time, because the clocks aren't related. And so it is almost the truest definition of asynchronous, where nothing is synced up, nothing can even be related to each other. And so the difficulty and the complexity comes in understanding the environment in which data and operations exist, and knowing on how to transfer data from one domain to another to have data appropriately measured in, or calculated in under one clock domain, and then using that data for maybe calculations or combinational or sequential logic in a different clock domain. And getting that data across can be really scary and also, frankly, dangerous depending on depending on the system, because you don't want a fire jet, like a fighter jet, excuse me, reading GPS coordinates and the GPS data come in muddled and just be completely wrong.
Yeah.
And so there's a lot of complexity inside it, and the reason why it's so hard is because the FPGA is, at its bare bones, a fabric of computer architecture parts that we are stringing together to communicate. And this is one of those things where the FPGA cannot figure it out by itself. You have to intelligently tell it and make it understand how, or make the design appropriate and appropriately understand and handle how to move this data from one domain to another. Because the FPGA compilers and FPGAs themselves don't have any catch or like safety net for this, because there physically can't be one. And that becomes there's some like graduate level physics to explain this on why they can't have a safety net, and that's a little bit above anything we're doing in that specific field. But it's like there are, like, real physical limitations that literally come down to like random electron clouds that can lead to something called metastability, where the data is not only wrong, it's genuinely random. And so that it can cause some major issues. And the difficulty is that you have to understand at least the principle of it to be able to handle this appropriately, because there's nothing that does it for you, if that makes sense.
Yeah. No, Ryan, honestly, that's a great description there of how that works. Even I understood it. I'm glad you didn't go into the advanced physics, but that was really good. Can you, just in case anyone hasn't listened to any of our previous episodes, Ryan, remind everybody what it is that you do over there at Concurrent?
Sure. Yeah. So I'm a senior hardware engineer, FPGA hardware engineer here at Concurrent Real Time. So I do a lot of the firmware and algorithmic designs that we have here. So whenever we're designing something internally for a product, or if we're creating a custom solution for a customer, I'm typically one of the main people doing the FPGA design and doing the firmware design inside the FPGA.
Charles, did you feel like Ryan's description was pretty good there?
Yeah, it was excellent. He did a great job. It's the clock crossing is a very challenging problem for FPGA design, but it also, I think, elucidates some of the benefits of an FPGA and how we can have such low latency. Some of it can be a very manual process, But when you have that combinatorial logic and you very carefully think of how you're registering things and how you're clocking things, you can have a very clear fixed number of time cycles, as you was suggesting, if you're counting on a clock, guarantee that the data from the input and the output is valid and accurate. So it does require experience and knowledge, but it's vital, and it really does kind of show why um, the latency part is so important. It's hard, but it's incredibly valuable. And to have that super low latency in FPGA is incredible, and one of the major reasons why it's closer to an ASIC, an application specific integrated circuit, than GPUs or CPUs, which are much slower in terms of latency.
And remind me what you remind everybody what you do over there at Concurrent Real Time.
Yes, so I'm the FPGA workbench manager, and my areas are, I do FPGA design and signal processing.
Awesome. All right, so we got a little base. You gave us kind of the overview of this concept. What are some of the mistakes that you might see when it comes to clock domains, when it comes to the clock domain crossing?
Sure. So one of the biggest mistakes, and typically one of the most common mistakes, is people will just ignore it in the sense of, all right, well, we have this data on the FPGA, it's running at a certain clock. As long as I send it to the other clock, everything will be fine. And there are cases in which it works out just fine, because the issue is when the information travels over a physical distance of a wire inside the FPGA, and it becomes a genuine issue of light not being fast enough, like light speed not traveling fast enough because of how fast these clocks are iterating. Sometimes that distance in which the information is traveling is so close to where even if you miss like the exact time, you won't see any random or muddled data. And at worst, what happens is if you're sending a stream of 1 million data points, what might happen is you get 1,000,001 data points or 999,999 data points. There's one off in either direction. And in the case of you missed one, oh no, you just lost one piece of data. Who cares? There's 1 million others. Or in the case of getting 1 million plus one, you have one piece of data that's duplicated. And in that case, it's like, all right, well, it really depends on how mission critical your design or system is. Because, if you don't care that sometimes a piece of data will be duplicated, who cares?
Right.
Like that, then there you go. Then it is the perfect playground to make as many mistakes as you want in clock domain crossing. And so a lot of times, whenever designers are learning to code with FPGA or coding certain algorithms or projects or processes that don't require perfect accuracy, perfect latency, and no data duplication or loss or decimation of any kind, they kind of will have this habit of not really caring about the clock domain crossing, because the chances of them having any issue at all are genuinely close to zero, especially if the clock rates that they're operating at are well below the maximum spec of the FPGA. And so a common mistake is that to think that certain things that can work at a low level, not necessarily low level, but more of a slower design, are going to work at the cutting edge optimal parts of the FPGA. A play that you can run in high school football might not work in the NFL. And so I'm just being honest here. And so, in the case of moving faster clocks and more complex designs and more resources on the FPGA being taken up, it is very common for engineers to be lazy and think that their bad habits that they learned in the slower, less responsive, less intensive designs will work in these cutting edge, really impactful, really dense designs, if that makes sense.
Mm-hmm. Yeah, no, the football analogy is good too. I mean, you're a Gator, like a lot
Go
of
Gators.
a lot of those plays do not work in the pro, for sure. As fun as they are to watch. So, how does your team approach this? Is it more about design experience? Are there tools that help? How does it work?
So there are a lot of research papers and white papers on how to handle this appropriately and how different situations can be handled in certain clock crossings. Like, for example, a 1-bit piece of data in comparison to a multi-bit piece of data are very different handlings. And so the tricky part for our group is we have created a product that is generic. The idea of FPGA Workbench is for the customer to be able to drag and drop what they want and do what they want to do, and for us to be able to programmatically have everything handled. And so the difficulty is that a lot of the ease that comes with clock domain cross handling is that you know what your design is and you know the domains you're crossing from one to the other. And so you can specifically handle what you want to do. In our case, we're having to isolate all possible cases of clock domain crossing that a customer could do and make sure that we have embedded solutions inside of our designs and architecture for that, so that a customer doesn't come back to us and says this data is random and muddled and metastable and nothing's working. So the way we've handled it is, firstly, all of our clocks are on the same domain. That is, it is very important that we have based the architecture inside of the FPGA that holds all of our designs or potentially customers' designs, where every clock that is available to them is on the same domain, such that even if there is some different rate that they're running or any issues that they might potentially would have run into if they were on different domains, they're all on the same domain, so that whole problem is avoided entirely. But specifically for upsampling and downsampling, customers can run into issues where we allow the customers to pick whatever clock rates that they want. In the case of maybe they want one clock running at 100 megahertz and another clock running at 37 megahertz. And so this ratio between the two clocks isn't an integer ratio, because like 100 divided by 37, you're going to get some decimal number.
Yep.
And so what that causes on the FPGA side is the clocks don't really line up as cleanly as you might want them to. In the case of a seconds and minute analogy, the seconds occur and then the minute occurs every 60 seconds. And so when you watch the second hand go around the clock, when you know the second hand gets to the top of the clock, you know that's when the minute's occurring. Imagine if a minute was 2.75 seconds. It'd be a little harder to kind of like, know when the minute was happening just on the shape of the clock. So what we've done is we have implemented some asynchronous FIFO algorithms, and FIFO being first in, first out algorithms, where you can intelligently downsample and intelligently upsample with some filtering that we do and some CIC filtering, where the customer can interpolate the data or smooth signals out whenever you're upsampling, or intelligently decimate the data, aka remove certain data points when they're downsampling, such that we intentionally throw out data at a specific ratio or rate so that the data is valid across the change of clock frequency and integer ratio, even if there's not a clean ratio or clean change. Now, a lot of the solutions that we do are able to be implemented because we're all on the same clock domain. A lot of these would have a significantly higher layer of difficulty and almost impossibility to try to do, to allow the program to figure out, how FPGA Workbench to figure out how the customer wants to do it. And we eliminate all of that complexity by putting all of our clocks on the same clock domain, and then isolating these specific cases of downsampling and upsampling, and allowing the customer to specifically use these aspects in design inside both the architecture and our IP library to handle every possible situation they could have.
All right. Charles, anything to add?
Yeah, so I guess this also kind of highlights that when you're doing FPGA development, it does require a number of different skill sets. When you're dealing with clock crossing, or there's the SDFC, you're making sure you're dealing with timing very carefully. It's usually kind of a lower level perspective on the development, where you're looking at the clocks and metastability. And then there's the higher level side of things, and that's traditionally a little bit more of an FPGA engineer. And then the higher level, where you're looking at it from a signal processing perspective, where you're looking at the actual waveform, and you're looking at concepts of like Nyquist frequency, where you have to sample at twice your highest frequency component. And then if you're going to upsample or downsample, you have to have a pretty clear idea about how you're going to filter that. There's aliasing when you downsample, where signals get aliased into your desired signal. And when you upsample in time domain, right, you're upsampling, then you need to filter it, which removes sharp edges, which spectrally is removing what's called the image. So there is sort of it's a complicated problem, and it requires knowledge from a sort of a higher level signal processing perspective, where you're looking at how are signals resampled and what do they look like in the time domain or in the frequency domain. And then there's also the lower level challenge of just managing all the clocks and figuring out even how they get routed, and then kind of gets into timing as well. But it's a hard problem, and we try and handle, as Ryan suggested, we handle as much as we can, especially with managing integer upsampling and integer downsampling. Fractional order sampling is a little bit more challenging, but yeah. So that's one of the benefits of the tool as well, is that it kind of alleviates most of the challenges that a customer may have if they need to change the sampling rate of their signals.
Interesting stuff. It's definitely something this is new to me, and you guys did a really good job of explaining it. So thank you for that. And thank you for joining us on Inside the Logic, real talk with FPGA engineers. Special thank you, as always, to Charles Sobczak and Ryan Erickson. Thank you guys so much for being here. It was great chatting with you.
Thank you, Kevin.
Yeah, thanks for having us.